Today I'll be talking about federated learning and also our DL project report. So federated learning is a modern machine learning paradigm designed to train model while preserving data privacy. Traditionally, machine learning relies on collecting data from multiple users or devices and centralizing it on a server where a very good model is trained. However, this raises serious concerns about privacy, security and data ownership, as the central server needs the data from all the clients. Federated learning solves this by bringing the model to the data or some form of knowledge to the data without sharing the raw private data. This helps to preserve privacy of the clients while also training a good machine learning model. So in federated learning, multiple clients, for example, mobile phones or banks, etc., train a shared model collaboratively. How it works. A central server sends an initial model to all clients. The clients train the model locally or try to make generate some form of knowledge signal, which is then shared to the server. The server then aggregates all the knowledge signals or the models to train its server model and then send this new updated model to all the clients again. This step is repeated again and again iteratively. Uh, the key advantage of federated learning is that the raw data never leaves the client, which improves privacy and reduces communication of sensitive information. Despite its advantages, federated learning comes with several challenges. First is communication cost. Since training happens over many rounds and involves sending models updates frequently, the communication overhead can be very, very high, especially with large and complex models. Second, system heterogeneity. Different clients may have varying computational power, network speeds, or availability. Some devices may drop out or be slower, which complicates training. Third and most important is data heterogeneity, also called non-IID data. Unlike traditional ML, where data is assumed to be identically distributed in federated settings, each client may have data from different distribution in real life. For example, one client may only have images of cats and another only dogs. This leads to unstable training and poor generalization of the global model. And last, although federated learning provides data privacy securities, attackers may try to still attack the data in many forms, such as membership inference attacks. So, since there are iterative communication, the attack surface is very large. To solve some of these problems, one-shot federated learning is used. In this approach, instead of multiple rounds, each client trains a model locally only once, then sends the trained model or some form of representation or knowledge to the server. The server then aggregates these models or knowledge into a final global model. This drastically reduces the communication cost from many rounds to just a single communication step. Also, since there is only one communication step happening, the attack surface for attackers is very small. But there are still some problems in one-shot FL. For example, the server cannot correct if there were any errors from the clients, or poor local models can negatively affect the final global model. Given that, one of the best or most well-known methods used for one-shot federated learning is that the clients try to train variational autoencoders or some form of generative models on their local data, which is shared to the server, which then uses this model to generate synthetic data to train its global model. But there are a few problems with that. Uh, first is that feature space heterogeneity. So all clients have different feature spaces, so different data. So combining them can be harmful for the global model. And second, there is severe data scarcity. Like some clients will not have enough data to train the variational autoencoder. So our method which we are discussing, FedVIP, it tries to solve one of its problem, which is basically personalizing the variational autoencoder to improve the quality of synthetic generation on the server side. So now Meet will take over and explain how FedVIP does this. कर लेना.
So now we have a new problem. If you only get one shot, how do you train a good model when each client has a very different data and very few samples? That's the exact problem FedBeam is designed to solve, using latent diffusion model to generate high quality synthetic training data. Let's walk through the pipeline. So looking at the diagram, you can immediately see there are two worlds. First is the client side, second is the server side. The client side, shown in blue, is where the private data lives. The client does all the local work here and never share its raw images. On the right, the central server, shown in the B. This is where the powerful pretend latent diffusion model, think stable diffusion, lives. The server receives compact information from client and uses it to generate synthetic images for training a classifier. Now let's zoom into each side. So first, let's go by the client side where we have instance level personalization. So the client has two local images. Let's call them xi and xi prime. Both of the same class. In our example, both photos are of dog. Each image is passed through an autoencoder denoted as E, which is VA encoder from the pre-trained latent diffusion model. This compresses each image into a low-dimensional latent representation that is shown over here. Now, let us go on to the concept level personalization. So you can see the text prompt at the bottom. A AS style of V. Here S stands for the domain name and V stands for a domain concept such as QuickDraw or Sketch. These placeholder tokens S and V are not fixed words. They are learnable embedding vectors randomly initialized and then optimized directly on client's local data by minimizing the standard diffusion denoising loss. Critically, this is a key efficiency win, and the client is not fine-tuning the entire latent diffusion model that would be computationally prohibitive on an edge device. Instead, it's only optimizing these two small textual vectors. The LDM weights stays are completely frozen. After local training, client has captured domain essence in these compact vectors. This, along with the noisy latents, are packed up and sent to the server in that one single shot upload that we have shown over here. Now let us move on to the server side. This is where the magic of generation happens. Server receives two things from the client, the noisy latent vector and the optimized concept vectors. The latent space, look at the top of the server box over here. The noisy latent space is fed into the UNet, denoted as theta, which is denoising network at the heart of stable diffusion. Its job is to gradually remove noise over T steps and reconstruct a clean data diffusion model that is a standard diffusion model inference. Now, simultaneously, at the bottom of the server, uh, built using the client's uploaded concept vectors S and V, is passed through text encoder. This produces a text embedding that conditions the unit on the right style and category. So denoising doesn't happen blindly. It's guided towards generating, say, a quick draw style airplane. To add more diversity, server also adds a tiny random noise to the domain vector S before generation. This prevents all output from looking identical. The clean latent is passed through VAE decoder D, which maps it back to pixel space, producing a synthetic image X. This synthetic image, paired with own label, is added to synthetic dataset D, as shown over here. The server does this from every client's uploaded vectors, generating a rich, diverse pool of synthetic images that together cover all the different client domains and classes. Now, stepping back, why does this whole pipeline actually work? So, this is due to the concept of division of labor. The noisy latent carries instance-specific fine-grained appearance of client data, the exact texture, shape, and structure, while concept vectors carry the high-level semantic meaning. Neither piece of information alone is enough for generation, but together they allow servers frozen LDM to synthesize images that genuinely look like they came from client private dataset. And that's the FabBip pipeline, a beautifully designed system that combines instant level and concept level personalization to solve one of the problems in federated learning. In our extended work, we further go by replacing the continuous VAE with VQVAE and applying a 16-bit quantization to cut the upload cost by over 60%. That further will be extended by Mayank.
The single most important parameter that everyone tries to optimize. And this has translated to deep learning too, where everyone tries to optimize on the accuracy. But in federated learning, this is not the case. In federated learning, models are trained across multiple distributed clients that can be phones, edge devices, or local machines without sharing raw data. This completely new setup introduces a completely new different constraints. Not just how accurate the model is, but also how efficiently these different nodes communicate with each other. Because every training round or every training epoch involves transmitting model information between clients and the central server. And this is where things start to break. So let's quantify the issue here. Most standard implementation use FP32 precision, which means each parameter takes 32 bits. Now imagine a model with millions of parameters. Every round, you are transmitting megabytes of data per client. Multiply that across hundreds or thousands of clients, and the communication becomes the bottleneck for the privacy. This high amount of data being transmitted at each epoch becomes the honeypot for the attackers to extract data illegally. We we are trying to optimize on it. So even if your model is highly accurate, it may be completely impractical in real model deployment. So in federated learning, we need to optimize for two things: model performance, obviously, but also the communication efficiency, which is the bandwidth and the transmission cost. And often these two are in tension with each other. Improving on one results in the decrease of the other. So we have identified two gaps in the existing approach of FedWeb. The first is the use of FP32 representations. FP32 representations send 32-bit signals for each parameter. Now these may be said that it is essential since the knowledge transfer is required, but the use of BF16 or FP16 provides way better communication cost with a small trade-off for the knowledge loss. And uh, and and using FP32 for the millions of parameters lead to high redundancy and also a high dimensional latent representation in the variation autoencoders used here. So our approach is to address this problem from two separate angles. First is the simple approach of reducing the FP32 to a BF60 or an FP16 representations. So this immediately cuts the communications cost by nearly 50%. And the most important thing is here is this reduction comes with, of course, an amount of degradation in the performance, but which is very minimal. The second approach that we are employing here is the use of VQVAs instead of normal variation autoencoder. So why are we doing this? There are three main points where VQVA beats the traditional variation autoencoders. First is that it discretizes the latent space, which means that while sending the information, we need not send the whole latent vector. Instead, we can send a simple index. And as you can see here, a simple index of the VQVA is even better in communication cost as compared to FP16. Also, the VQVA uses representation of data using a code book of embeddings. This code book can be made available to the server, which in turn simplifies the whole problem. And also the problem of continuous redundancy that is often a problem in normal VAs, it counters that too. So uh, summarizing our approach, we have made this process more compact, more structured, and way more communication efficient. As you can see here, the results, FedBip using FP32 representations had to upload 10.6 megabytes for each iteration. But using VQVI and FP16 instead of FP32, we have uh, we have reduced this to just 2.9 MBs. Comparing this to the initial original approach, this is a way bigger improvement that anyone could have expected. So let's see how we have made that these changes in the code actually. Here you can see that we are enforcing the model to use float 16. Using a BF16 could be a better approach here. Probably we'll employ it, but there's a restriction on BF16 that it works only on the newer GPUs. So float 16 provides a more general change. Also, the second thing that we did is input using VQ model instead of an autoencoder KL. So you can see here the implementation. We are using a VQ VI model instead of a normal VI model, which is also pre-trained. And uh, this is where we are trying to uh, optimize on the bottleneck that the FedWip introduced. Another change that we have done is saving the model using dot half. This saves the model in 16-bit instead of traditional or the original 32-bit representation that significantly reduces the communication cost. So let us now see what results we have obtained using these changes. So we use PSES dataset for our experiments, and as expected, we were expecting a decrease in the classification accuracy. But as you can see, we are within 95% of the FedWip, the original accuracy. We got a reduction of 3 to 4%. But if you see the communication overhead reduction, it has been the it has been a way better approach in the communication department, and we can see that reducing the communication overhead from 10.6 to just 2.9 is a very big jump that significantly reduces the communication cost, and this makes it feasible to deploy on constrained hardware such as Raspberry Pi or smaller devices. So let us also see an ablation study on how the different types of models perform. So in the original paper, in the original paper, FedWip has obtained 62.67% accuracy with a 10.6 megabytes of overhead. But use but the we see improvements just by introducing FP16. We are seeing a drop of accuracy to 58.54, but we also see a drop in the communication overhead of 5.2 5.8 MBs. Introducing just VQs also introduce accuracy drop, but again we are seeing a communication cost drop, and employing both of them reduces the accuracy but drastically improves the communication costs. uh, if so Summarizing our results, uh, it's always been it's always has been the trade-off between the accuracy and between the privacy and the communication costs. So in our approach, we are trying to work more on the privacy and the communication part with a trade-off on the accuracy. So concluding our approach, I want to highlight few main points that we have done here. The first is to highlight that accuracy alone is an incomplete metric in federated settings and cannot be accounted for individually when dealing with such problems. Also, that communication cost is a first class constraint and cannot be ignored. Existing approaches using FP32 and VIS are very inefficient, and introducing our more complex models like VQVI or introducing FP16 or BF16 approaches can significantly reduce the communication costs. And these all can be done while maintaining a competitive performance. in federated learning tasks. This is how we can scale them to a real world system, and we need to to optimize models in isolation and start optimizing systems as a whole. So that's it. Thank you for this.